I'll go ahead and share my screen. Just one second, everyone. And that should do it. Welcome, everybody. Again, another day that we've got to be asynchronous, but this should be the end of it, I guess. We'll just jump right in. This is lecture 20. We're continuing our discussion on linear regression. Okay, so we'll just jump right in. Before I go any further, we've got exam three coming up. Okay, exam three is a week from today and it's in person, but it will be delivered on Canvas as we've done before for our last two exams. Okay, so again, a week from today, so that would be Wednesday, November 12th, in person, 100% on Canvas, all right, independently of my leg, it will be in person. If I will be there, if not, there will be a chaperone. Please plan on showing up Wednesday on Canvas. Obviously, one important point for the Biology 3003 section, this will be in our newly assigned room that we haven't all visited in person together. We're supposed to be there today. So just keep that in mind, okay? Section Biology 3000, Section 07, it's in the same room where we've been meeting all semester. Okay, reading for today's is chapter 8.3 and 8.4. Practice exercises are as follows. Um, let's see, Monday, you got your video exam and then a lab opened up and a problem set you have opened up too. So we're looking at lab number 8 being due on Friday at 1 p.m. as always, and problem set number 9 being due on Thursday, the 11th hour on Thursday, late at night, just for your convenience, okay? Okay, so back to our business here. So we've been talking about this idea, right, of capturing relationships between numerical, continuous, predictor variables and response variables, right? So again, these relationships are never truly linear in a sense, right? But they can have a linear trend. And if you draw a line, right, that's just an abstract mathematical model through that linear trend, that line is then giving you predictive power to then look at values of the predictor variable and what the response variable may be for those values. So that's the strength of linear modeling, right? So it's a linear regression that we're talking about specifically. And again, it's not terribly complicated. We've been exposed to the equations for a line for a very long time. I would say middle school. Um, we all learn what a slope was, right? The rise over the run, what a y-intercept is, right? Like that's the value of y where the line crosses over the y-axis. And yeah, I think that this is an incredibly powerful mathematical tool in order to be able to make predictions, right? About values of X and how those values of X may influence or to what degree they predict the response variable value. So yeah, X axis once again is usually our predictor variable. Our response variable is then consequently represented on the Y axis. And the equation of a line is more or less what we call their model here. So again, this equation of a line includes two main model parameters. Beta naught would be the y-intercept that all the data in a given population of observations, right, would give you. And then beta 1 would be the slope for that same uh, line model on all the possible observations. There's an additional term here that we ignore at this point. That is the error. So we'll not worry about the error at this point. Anyhow, just hearkening back to the example or one of the examples that we covered on Monday's lecture, we have this, right? So this is a possum or a bush-tailed possum, and we're every dot here represents an observation of one of these animals, and those observations, or for every time an animal was observed and plotted here, um, basically it's a total length in centimeters. So that would probably be from the end of the snout till the end of the tail, was recorded along with its head length. So again, base of the skull to the end of the snout in millimeters. So that's the relationship that we're looking for a trend for here. Again, particular value of body length is associated with the specific value of head length, right? And this, again, the relationship between total length and head is estimated by the following, right? You can draw a line through all of these observations, right, in order to estimate the relationship. Again, no one observation truly falls on that mathematical object, right, that line. But that line is supposed to more or less capture the net trend of the relationship between total body length and head length for these bush-tailed possum data set that we have plotted here. So anyway, that's a basic idea of what we're working with here. And again, we can come up with the line to estimate that. Okay, we haven't really discussed how the line is made, right? But I guess we talked a little bit about eyeballing it and wanting that line or eyeballing it and agreeing that the best fit line is the line that's the closest to any given observation of the data set. So again, if just pretend you're eyeballing that line, get it right across the middle of all the observations, that or if you eyeball a line that goes right across the middle of all the given observations, that will be your line with the least errors, right? Or the lowest possible residuals across, and that's usually what we consider to be the best fit model, okay? In this case, that would be the equation there. So again, your estimate for y hat will be equal to 41, which is the y-intercept for that black line, plus 0.59, that is the slope for that black line, times your predictor variable value, x. Thus, for a possum of total length of 80 centimeters, all right, in body length, we would predict a head length of 88.2 centimeters, right? Based on that line as the relationship between the two variables that we're interested in. Again, consider 88.2 millimeters an average, or I guess we would interpret this as a consideration of 88.2 millimeters, an average reasonable estimate of head length based on the total body length. Okay. So again, that this would be a hypothetical scenario where we have data for a possum collected years ago, for which there is a snout to tail measurement, but there wouldn't be a specific head measurement, right? If we have this model, we can then use this model to predict the most likely head length for that possum that for which the head was not specifically measured, but the body was. And that would be one possible application of this model. Okay, we had a brief, or not brief, actually, we had an extensive conversation last time about residuals, right? So let's just quickly go over this again the next minute or two. So residuals are the difference between the observed and expected values for the response variable, okay, for a given x. So the residual of the ith operation of x of I and y of I is the difference of the observed response, yi, and the response that would be predicted based on the model, y hat I. And again, it's more or less an encapsulation of the error, right? How well the model is doing in giving you the actual true value of head length for that particular x. So that's literally what a residual is encapsulating here. Again, we write that as E sub I equals yi, which would be an actual observation of head length for a given body length, right? Minus y hat I, which is the predicted value of head length for that same body weight, for which you have a true head weight measurement. So we typically identify y hat I. Remember, everything with a hat is going to be a model prediction from now on. Okay, so this is a response variable prediction based on the model. So we identify that response variable prediction based on the model, this y hat I, by plugging in the value of x associated with the known measure head value, right? That would be yi, this one right here. So again, say that we have this observation, okay? We actually went out to the field, capture one of these bush-tailed possums, and measure its body length in centimeters, measure that as 77.0 centimeters, and also measure for that same animal its head length in millimeters, 85.53 millimeters, okay? Or 8.53 centimeters, so we wanted to keep the same units. Anyway, long story short, right, here we have an X for here we have a data point actually, all right? So 77.0, it's right around there. And we have an actual head measurement for that body length, okay? And that would be 85.83 millimeters right here. So that's a true observation there, all right? And that's denoted by this X actually. And this plot, this came right out of your book actually. And that what we see is that this best fit line that we're considering to be the line that we've eyeballed to have the lowest residuals possible is slightly above that, meaning that if we were to plug in this value, right, 77.0 to get a y hat of x or prediction of a response variable based on that x, we would be getting a prediction that's slightly higher than what the true head length for that animal was. All right. So again, the residual is just the difference of those two, right? The sign of the residual, right, positive or negative, is a will tell you the directionality, right? Is the model overestimating head length for a particular body for a particular body length, or is the model underestimating head length for a particular body weight? All right, I think AI just triggered a hand being raised here by me, which was not my intention. Okay, let's see. All right, I'll lower my own hand. It's just distracting. Anyway, so again, a negative residual means that the model has made an over prediction, and that's what we're seeing here, right? When we subtract that from that, right, we're subtracting the actual y value minus the observed head value. We end up with a negative value here, meaning that the model is going to give us a head length for that body length that's slightly higher than the true body length for an animal of that same length again. So again, it's an error measurement. Okay. All right, we talked about something called a correlation coefficient, right? And the correlation coefficient is basically how linear uh, a data set is, all right, once plotted in a 2D axis. All right, so again, you can have positive or negative correlation coefficients. If the correlation coefficient is positive and it's a 1, that's a perfectly linear relationship, like you would see here. And it's also a positive linear relationship, meaning that as you go up in value, in your X, you will go up in value in your Y. Okay, so again, that's an R of one. And it's extremely rare to find something like this in nature. There might be some phenomena in physics where that happens, but even when you have predicted perfect relationships, even in physics, right? There's measurement errors, so there will be variation, but an R of one is extremely rare. And I'll be um, very sus if one of my students gave me anything really, at any time in my career that had an R of 1.000. Okay, just letting you know. Again, conversely, if you have an R of negative one, that implies that as you increase your values of X, your values of Y decrease, right? So it's an inverse relationship to what we had before, but it would still be perfectly linear and rare. Okay, what you would usually see is if you have a really tight linear relationship, either positive or negative, would be R values in fractional R values of zero point 0.9 something, right? Zero point 0.9 or above is extremely tightly linearly um, uh, or tight linear relationships that are summarized by that. And again, as your R value, negative or positive, it goes further and further away from one towards zero, then you've got just random scattering. All right. And again, here you can pretty much see a linear relationship too, but the residuals would be huge here, right? Same thing there. So again, the value or the sign of y tells you the nature of the relationship, if it's a positive linear relationship or a negative linear relationship, and how close you are to one tells you how close you are to perfect linearity. You should never really have perfect linearity in any process where you're measuring data from the world. Okay, but yeah, so a very low R value of, for example, here you can see negative 0.88 is nearly complete random scatter with no predictable linearity and let alone the slope at all, right? And like I said before, if the best line that you can draw through something that's completely random is a flat line, that means that at any value of x, you will have the same output of y, and you don't have any predictive capacity with your model. The slope has to not be zero, basically. Okay, line fitting continued, right? So we keep talking about fitting the best line, right? And I just said on Monday and a little bit today to just eyeball it, right? And actually, eyeballing it works pretty good. I would say that every time I've eyeballed a line, assuming that there was no outliers, we'll get to that too. I've done a pretty good job, okay, at minimizing the residuals, but there has to be a way to formalize this, okay? And there is a way to objectively formalize this line fitting routine that we need to basically have an unbiased definition of a good fit of a line, okay? This objective best line fitting, okay, has to be the line, like I mentioned, that has the smallest possible residuals. All right, so that is our canonical definition for what's the best fitting line across a bunch of linearly related data points. The best fitting line, once again, is the line that allows you to have the smallest possible sum of the residuals. Okay. So again, in this case, again, don't mind my super sloppy cartoon here, but that X is a predictor variable, Y is a response variable, black dots are data. Okay. The yellow line would not be the best possible line fitted through this data set, right? And that's obvious. Then the reason for that is that if you were to count all the error, right, the distance between that line, which is the model, for any given X, where there are observations of Y, right? That's a lot of summing that you would have to do, right? Maybe a couple of these observations, that one, that one, and that one, and that one would have very low error or low residuals, but most of the observations, especially up here, would have incredibly large residuals. So again, that would not be the best line to fit to this data set. Similarly, the red line would not be the best line to summarize the relationship of this or the trend of these data, right? Again, you would have an equal issue with the residuals just going the other way, right? Like a lot of model over predictions in the X line, a lot of model under predictions in the yellow line. Again, what you would be aiming for, and this is one more time eyeballing, right? It's just something right in the middle, right? And this blue line would have much lower total sum of residuals. All right. So that lower sum of residuals means that it's it's a more it's a model with more strength because it carries less error, essentially. All right, so again, in practice, we use the smallest square of the residuals or the least squares line to, or we use the least squares line as our best fitted line, okay? With these concepts as the um, as the criteria for what is the best possible representative line, uh, encapsulating the true trend of the or the true relationship between the predictor and response variable. Okay, so that's what we will do that. Okay, this is again right out of your book. Why do we use this? It is the most commonly used method. Okay, again, that's a book. I'm not sure if that's the best. I'm not sure that's a good response for anything, right? Just because everybody's doing it, that's not why we're doing it. So I guess the second point here is a more compelling reason why you would want to do this. Computing the least squares line is widely supported in statistical software. That's true. Okay. In many applications, a residual twice as large as another residual is more than twice as bad. Okay. Okay, and that's the reason why we squared the residuals. So we add the sums of the square of the residuals, okay, um, in order to see how well a line fits. And again, the reason for that is because we want to exaggerate differences, right? If something is twice as big of a residual, right, it usually doesn't mean that the error is twice as bad. It probably means that there's more underlying issues. We just want to exaggerate any deviation as much as possible, right? So squaring the residuals accounts for that. Okay, so that's why we use the least square lines of the residuals or the least square sums of the residuals, not just the sum of the residuals. Okay, so again, the first two reasons are largely for traditional convenience. Okay, the book's open about that. Yeah, that is tradition and convenience, right? Everyone's using it, and most free statistical software does this pretty easily. Yes, tradition and convenience. That's not because something's right. But the last reasons explains the true criteria of why it is this path is the most useful. Okay, it's just super straightforward to calculate all the residuals, square them, and then come up with an unbiased measure of how well that line fits all of the data. Okay, so all right, that's good. Of course, there's always conditions, right? We can't just jump into methods without delineating conditions, right? One of those conditions is going to be linearity. All right. There's many ways to check for linearity, but yeah, looking at a residual plot, right? If it has some sort of pattern, you know that it's not going to be linear, so on and so forth. Okay, we'll talk about this in more detail in just a second. Yeah, you got to have nearly normally distributed residuals. That's a super important point also. And again, residual plots will show what that is, right? You want equal scatter above and below the zero residual line across the entire range of your values for your predictor. So that would give you a good sense that you've got normal residuals. You want constant variability, right? So you wouldn't want to see a trend in terms of how tight the data fit a line for a certain range of X, and how and then that tightness dissipating as you go across the range of X for whatever reason, like you see here, this coning. All right. So be actual coning on the data above and then coning on the residuals below. That would imply not normal variability. Okay. And obviously, you want to make sure that you're independent, that your observations are independent. So if you see a pattern, right, a sinusoidal pattern, any kind of pattern would imply that there's probably a confounding variable or some other thing affecting the value of your um, response in addition to your predictor variable. So it wouldn't truly be independent in that sense. Okay. All right. So how do we go about fitting this least squares line? Okay. So again, fitting the least squares or finding the least squares line is as follows. Okay. First thing that you've got to do is have your estimate. So that is usually y hat, but in this case, y we know it's the response, so it's response hat equal to beta naught plus beta 1 times your predictor. Okay, so again, this is kind of like the linear model formula. Okay, all of these parameters, right? Again, the parameter is beta naught and beta 1, the y-intercept and the slope. All of these parameters have to be estimated. So we need data in order to estimate these parameters. All right. So again, the estimated parameters from actual data are annotated as follows. Beta naught, Greek letter beta naught, which again is the true parameter, is estimated by data that we can gather from the real world and then annotated as lowercase italicized lowercase b naught. Okay. This slope parameter, uh, capital Greek beta 1, is estimated with our actual data and then further annotated or subsequently annotated as lowercase Latinized bi or b1. Okay, again, b naught is the y-intercept estimated from the data, and b1 is going to be the slope estimated from the data. Okay. So first things first, what you're going to want to do is find the slope. Okay, the slope's a pretty important criteria for the two parameters that determine the that help you draw a line. Okay, and the slope estimation is quite easy actually. Again, the parameter, the true slope, right, would be beta 1. And we're just not going to work with that ever. What we work with is an estimation of that parameter, which would be lowercase b1, right? And this lowercase b1 is quite straightforwardly estimated by simply taking the sample standard deviation of the response variable s of y and dividing that by the sample standard deviation of the response variable. Um, oh yeah, this should be, sorry, S of y is the sample standard deviation of the um, response variable. Yeah, that's correct. S of x is the standard deviation, sample standard deviation of the predictor variable. Sorry, I got those mixed up. So that's right. And then all of that is multiplied by R, which is the correlation coefficient between the two variables. All right. And all of this data will be given as far as I'm concerned. I don't think there's just not enough time in an exam to go do this by hand also. Okay. So, all right, again, this is our estimation of the most important parameter here, right? Like the slope. Very important to like draw a line. Okay, what would this look like in practice? So again, estimating the least squares line slope is, like I said before, the standard deviation of the response variable divided by the standard deviation of the predictor variable multiplied by R. Let's look at this data set now. Here we're plotting family income, okay, from 0 to $250,000 a year plus. And then as a predictor variable for a response variable of gift aid from a particular university. All right. Obviously, what we see here is a negative trend, right? The more family income a particular student has, the less. financial aid that will be available for them by this particular university. Okay, so I think that's a pretty standard financial aid model. Um, anyway, long story short, there's a line there, right? And we want to draw the best fit line. And in order to find the slope, to draw that best fit line here, we need the following, right? Um, we need the standard deviation of the response variable, which again, in this case is gift date is the response variable. So that standard deviation would be right here. $5,460. And we need to divide that by the standard deviation of the predictor variable. And the predictor variable would be family income or X. And that would be $63,200. All right. Lastly, we need to multiply that by R. And R is already given to us here. Also, R is negative 0.499. So again, not a perfectly linear relationship, right? We see that there's a lot of variance, there's variation, right? There's high residuals here. But it is a negative slope, that's for sure. And it's not at zero, at least, right? So it's nearly 0.05 or zero point 0.5. So you just bring that right in, R, and you multiply it times whatever you get from this division. At the end of the day, here you have a slope of negative 0.0431. All right, and again, this particular slope is going to be the slope that you want to use in your linear model. And that linear model is basically will be based on the or will represent the least squared line, right? The line that has the least error associated with it across that particular data set. So again, still got to get on, we got one more step in order to come up with that final model, but the most important step, in my opinion, the very first step should be coming up with the slope. And again, the slope is simply estimated, the slope of the best fit line specifically, okay? The slope of the best fit line that you want to use to model, okay, this relationship is the standard deviation of the response variable divided by the standard deviation of the predictor variable multiplied by R. Okay, that's what we have here. Next, we're going to use something called the point slope formula to finish our model. Okay, and the point slope formula is using a point that's already on the least square lines. Okay, and then writing the equation of a line based on that, using the slope that you got for the least squares line also. Okay, so again, just follow or just bear with me here. X hat and Y hat are the X, Y coordinates for a point that's already on the least square lines. Okay, so Y minus Y naught will be equal to slope times X minus X naught, where again, X naught and Y hat and Y naught will be a point that's already on the least squared lines. All right. All right, so what do we have here? Y minus Y hat will be equal to B1 times X minus X hat. All right, so Y is your predictor, it's your response variable, okay? So that's just states as Y. A point or the mean, all right, of your response variable and of your predictor variable, the means turn out to be actual points that are already on that least squares best fit line. Okay, so you can literally take the mean, all right, of your predictor variable and consider that a value of x. Okay, and you can take the mean of your response variable and consider that a value of y. And those two means are an actual point that's already on a line that corresponds to the best fitted slope across all the data points. All right, so that is again something you really want to remember, I guess. So again, the x and y coordinate for a point that's already on your best fit least squares line is gonna be the mean of x as the coordinate for x and the mean of y as the coordinate for y. All right, so with that in mind, you can simply plug in the values into this point slope formula. Okay, and the point slope formula, once again, is just y minus uh, a point or a y value for a point that's already on the line. And again, this would be the mean for your response variable right here, 19,940. is equal to the slope, which we just calculated, right, one slide ago, multiply by x minus an x point for a point that's already on the least square line, and that x point that's already on the least squares line is the mean of x, or the mean of your predictor variable, 101,780. Okay, that's what I've done right here. All right, so with that being said, it's just a matter of doing the arithmetic, right? Well, I guess you need to use the distributive formula here, right? So you need to multiply this by x, then multiply that times that to end up with this, and then add 19,940 to both sides to come up with this final equation here, which is y is equal to 24,327 minus 0.0431 times x. Okay, and that would be our model based on the least squares line. Okay, so again, this is our best fitting line, our least square line base model. Okay, and when subs or when better explaining what y and x are, we get the following, right? For the particular example where this data came from, right? We get the estimate of eight. That eight, that's what the little hat means. A little hat means an estimation based off of a linear model. The estimate of eight is equal to $24,327 minus 0.0431 times the family income in dollars. So that would be our best estimate. Okay, cool. So let's see. One second. All right, so we'll set up for a group problem here. Again, feel free to pause the video at any point. I would probably give you guys 2 to 3 minutes to figure this out in class, but pause your video at this point. Once I'm done reading this. Consider a regression model predicting weight in kilograms from height in centimeters for a sample of adult males. What are the units of the intercept, beta naught, and the slope, beta 1, excuse me, and the correlation coefficient, R? Hint, draw and label the axis of the scatter plot you would use to visualize this data. So again, feel free to pause the video now. All right, and let's jump right back in to see what these units would be for all of these model parameters. So again, you would want to draw this, right? So we've got the x axis as our predictor axis, right? And that predictor axis is height in centimeters. I guess this was a sample of adult males. The response axis would be weight in kilograms, right? That's our y-axis there. All right. If our slope, m, is equal to the rise over the run, we would be looking at kilograms as the units for the numerator, and then uh, centimeters, that the units for the denominator. So again, the slope for B1, or the slope of B1, would be kilograms per centimeter. Okay. Similarly, the y-intercept would simply have a slope. The y-intercept is just where x touches y, and again, at the y-intercept, x is 0. So you're only considering the units of y. And in that case, that would be kilograms. So again, our y-intercept would be kilograms, and the correlation coefficient would be actually unitless. Okay. Note, if you square the correlation coefficient, you will get the percent variation in the response that is explained by the explanatory variables. Yeah, that's a pretty useful hint here. And I go over that extensively when we do something called a multivariate statistics. But yes, if you square the correlation coefficient, you get something called the R squared. And the R squared is basically the amount of the variance that is of the total variance of the data set that can be explained by that one variable. Um, so again, the explanatory variable in this case would explain 94% of the variation in the response variable. Okay. All right, let's do one more together here. So this is a work problem. Yeah, let's go ahead and do this together. Again, straight out of the book. This is 8.25 in the book. Not the best of topics, but let's see what the data say right here. So we've got murders and poverty, part one. All right, the following regression output is for predicting annual murders per million from percentage living in poverty in a random sample of 20 metropolitan areas. So this probably means 20 large cities, right? There's uh yeah, for like that many murders per million, right? Okay, so we've got our data set there. Okay, our predictor is percent in poverty, right? So we're thinking that the murder rate is a function of percent of people that live in poverty. And this might be true. I don't know. I'm not a sociologist or anything, but it seems true for a number of different reasons, right? Horrible reasons. But anyway, all right, focus on the data here. This data appear to be linearly correlated, right? This slope is positive. And there's certainly tons of variation, right? No matter how you think that you can draw a line through this data set, there's always going to be some observations that are very high or very low, below or above any given possible line that you can imagine fitting through there, right? But anyhow, okay, all of the stats are computed for us up front, right? So we've got the estimate for both of the parameters. So yeah, what you see here is the estimate for both of the parameters, right? That first column estimate is your beta naught, the y-intercept, is negative 29.901. All right, that is the y-intercept, which is one of the parameters for the model. Okay, again, that is the first cell under the column of estimate. So they're estimating parameters. That's what that column represents. Okay. Um, the second row is percent poverty, right? And percent poverty will be our slope. Yeah, that is yeah, so that is correct also. Anyway, so what we want to do now is write out the linear model. Okay, yeah, just kind of jumping ahead, of course, already. We gotta interpret the intercept. All right, so like talk about what that intercept means as it is written there. We've got to interpret the slope. Okay, what does that slope also mean? And then interpret R square, and finally calculate the correlation coefficient. So let's go ahead and jump right in here. So, all right, part A is writing out the linear model. Okay, like I said before, all of our model parameters are already given to us up front. Okay, so all we got to do is put the equation together for a linear model, functional linear model. Okay, with the appropriate labels. So again, we've got the response variable, right? Response with a hat being equal to beta naught, which is the y-intercept of the model, plus b1, which is the slope of the model, times the value of the predictor. All right. Same thing we've seen all day today. So to write out the appropriate linear model for this particular question, we've got to do the following, right? So we've got murder rate hat, estimated murder rate is equal to the y-intercept, which again, from the first row of the first column is negative 29.901 plus the slope, which from the second row of the first column in estimates is 2.559 times the given poverty rate, right? Like where this question is being asked about on the x-axis, right? Poverty percentage, right? So that would be it for writing down our linear model. Okay, so that is the linear model A. All right, let's move on to B. Interpretation of the intercept, right? Expected murder rates when poverty is equal to zero is more or less what the slope is, the y-intercept, I'm sorry, is telling us. Okay, and in this case, right, we've got a negative 29.901 y-intercept. And in reality, right, you can have negative murder rates. This is truly absurd. It's just completely meaningless, and that's okay. You need a y-intercept in order to have the best possible slope. All right. But the best possible slope means that this will be meaningful and true to the best degree that the trend is captured by this data for most of the range of X, okay? But again, like getting that most meaningful, largest possible range, right, of X can have a line that means nothing when it touches the y-axis. So don't think into that too much. Again, you can have negative murder rates. So the y-axis, yeah, the y-intercept, right, of that line is truly meaningless in this case, and that is okay. Okay, so even though we have a completely meaningless absurd y-intercept, we know that this is the best fitting line. So we should have this same line that has this absurd y-intercept gives us the largest possible range of x, where we can have the best amount of the relationship between x and y capture and be informative. All right, so that's really the point of this. All right, so that would be my take on question B. All right, let's move on to question C, interpret the slope. So again, the slope is just the rate at which the expected murder rates increase per additional single unit percent increase in poverty. All right. So again, every time you go up 1% in poverty, I think yeah, percent's a unit of poverty, you will go up 2.559 units of murder rate. And like the specific units here were annual murders per million. So there's 2.559 more annual murders per million every time you increase 1% in poverty level. Okay, so that's interpretation of the slope there. All right, moving on to D, we're interpreting R square. Poverty level explains 70.52% of variability in murder rates in metropolitan areas, which is quite impressive. Okay, if you were to take other things into account, right? I don't know, education level, um, anything else you can imagine, right? Density of housing, uh, anything else that you can fit to this model, whatever else you bring in, right, can only explain uh, or only has 30% more of the space of the variation to be an explanation for. So this means that we're actually working with an incredibly strong predictor if 70% of the variability in the murder rate is actually captured by just this one predictor. So uh, that is an indication of this linear model being actually quite strong. Okay, and then figuring out the correlation coefficient. Again, correlation coefficient is just how tight of a linear fit do we have, right? You would just take the square root of r squared to basically render back r, and the correlation coefficient would be 0.8398, which again, anything close to zero point 0.9 is actually extremely strong. Okay. All right, what do we do here? Let's see. All right, looks like we got one more before moving on to a discussion of outliers and wrapping it up for today. Yeah, so let's go ahead and do this. The following regression output is for predicting the heart weight in grams of cats from their body in kilograms. Wow, it's another interesting setup. I don't know. I don't know which one I like better. Okay, the coefficients are estimated using a data set of 144, I'm sorry, domestic cats that obviously if they had their heart weighted, right, these are domestic cat carcasses. These guys didn't make it if someone weighted their heart, physically weighted their heart. But anyway, that would be the strength of this model, right? That if 144 dead cats were needed to generate it, but then now that you've got this line, right, that's supposed to capture this relationship, you can weigh a living cat and know to a certain degree, right, how much his heart alone weighs without obviously doing the experiment. But anyway, so we've got our same tabulated summary for the data set here. Again, we've got an intercept, right? The intercept would be one of our model parameters, the y-intercept. Body weight is our slope. So it's a second model parameter. The estimates for those parameters are your first column there. All right, you get other columns for error, t-value, and then an actual p-value. We'll get to that eventually, like how to do hypothesis inference based on linear models. We'll get to that. For now, we're just tasked with doing the same kind of question routine that we had in the last example. So again, we're even giving R square, right? So, all right, we're going to write out the linear model, then we're going to interpret the intercept, we're going to interpret the slope, we're going to interpret R square, and we're going to calculate the correlation coefficient. Okay, moving on. So again, the linear model here, super straightforward. You know that you want to be able to predict the heart rate. So the model prediction would be heart rate hat. Okay, and that would be equal to your y-intercept negative 0.357, which is right here, negative 0.357, plus your slope 4.034, 4.034 multiplied by the value of your predictor, body weight. Okay. All right. Interpret the intercept. A cat with body weight 0 is what the y-intercept would be highlighting, right? And again, it makes no sense whatsoever. A cat with body weight 0 is, what's this? Schrodinger's cat, right? It's there and it's not there at the same time. A cat with intercept with weight 0 will have an expected heart of negative 0.357 grams, which is again obviously absurd and meaningless. Don't think too much about the y-intercept again. Okay. Anyway, C would be interpret the slope, right? For each additional kilogram in body weight, we would expect the heart to be heavier by 4.034 grams on average. That's the interpretation of the slope. D, interpret R square. Body weight explains 64.66% of the variability in weight of cat's heart. So again, that's a relatively good predictor, right? There might be other things that can explain the body weight. Sorry, that can explain the heart weight other than body weight. But again, those other things can only account for 30 something percent of the total variation in the data set. All right. Okay, E would be calculate the correlation coefficient. And again, this is just a measure of linearity, and that measure of linearity is 0.8041. So again, tending towards zero point 0.9, which I'm saying is like extremely high, right? You never really get to one. All right, just to wrap it up here, just a few quick points on outliers. So there are some really detrimental outliers that we call points with leverage, okay? So all right, so leverage are points that fall horizontally away from the center of the cloud. The cloud means the aggregation of all the other data points and tend to pull harder on the line, all right? So these points are generally called points with high leverage. All right. Not good to have in your data set. All right. So let's have a look at this real quick. Uh, we have a point that's a bit of an outlier here, but it's not necessarily that far away from the clustering, right, of all of your other data. This is most of your data here, 99% of the data, and there's one outlier that falls somewhere in the middle of that clustering. It's not going to have a terrible amount of leverage, right? So it's going to be low leverage and not influential. Okay. Again, this wouldn't mess your slope up of like the least squares line that much. All right. Now let's look at this one here. Here we've got our cluster of data way up here. And then really far down the range on the x-axis, we've got this guy here. So again, this data point is not necessarily that far away from that line. So even though it's far away, it would be high leverage, but not tremendously influential on the kind of slope that you would measure with or without it that far away, right? The slope will more or less look the same across this cluster right here. So again, high leverage because it's far away from the cluster, but not influential because it more or less falls in line with the expected slope if it wasn't there. All right. This is the same thing here. We've got low leverage because we're right above the cluster, right? And not influential because it's not going to change that slope that much. All right. So in this case, we've got now scenario three, we've got a point that's really far out in terms of the range of the x-axis to where like all of the other clustering is happening. And on top of that, it is really off from the predicted slope that we would have before. And in that case, you would have a high leverage and influential data point on the slope that would be predicted. So this a point like this can really throw off your estimation, right, for what would be the true slope and drag it towards it more or less, right, or leverage it towards it. And that's what we mean by high leverage and influential. Okay. So what do I have here? Just a couple more examples here. Again, this would be a high leverage and influential cluster. Again, far away from the main cluster of the data set and definitely throwing the slope off to a high degree, high leverage, influential cluster of points here. This other guy here would be high leverage and influential as well, right? We would expect this one single point to change the best fitting line by a lot. Okay. So again, this would be the line in red without this point, and then what the line becomes after this point. So that's a massive change in the slope, right? So that's something to keep an eye out for. And then here we have a high leverage, again, really far away from the main cluster, but not influential because the slope's not changing that much with or without it. Okay, so okay, I think I'm gonna leave it at this. You're welcome. Obviously, there's homework problems assigned already for you to explore this concept of high leverage and influential outliers, okay, and how they might affect linear modeling results. But I'll leave that up uh, to your own time. It's already part of the homework. So, with that being said, thank you for your attention, and I look forward to seeing you all a week from today now on Wednesday for exam 3. Okay, take care, everybody. Bye bye.